Why do AI agents forget what happened yesterday? Honestly, it's the central question that absolutely plagues engineers the second they try to move away from building cute, toy LLM demos and into robust, production-grade systems. I mean, we've all felt that frustration, right? You build an agent, it works perfectly in your little testing window, but deploy it for a week, suddenly it's asking users for information they literally just provided 3 days ago. Here is the harsh reality. Reasoning without the right context is just expensive hallucination. The underlying models we use today, they've gotten incredibly good at reasoning, planning, and executing tools. But deploying those models without a concrete memory infrastructure is a massively costly mistake. If your agent doesn't have the context to know what was decided yesterday, all that amazing computational power is just burning tokens to confidently give you the wrong answer.
Welcome to the Explainer. Today, we are exploring Module 11, Production AI Systems, and specifically the absolute necessity of agentic memory. I am so excited to dive into this with you and figure out how we actually scale AI memory for production, looking at everything from databases and memory optimization to latency, scalability, and the enterprise guardrails required to keep these systems secure. Here's our agenda for today. We'll start with 1, why basic memory fails, then cover 2, the 4 agent memory types, 3, architecting for scalability, 4, knowledge graphs versus vector DBs, 5, optimizing cost and latency, and finally, 6, enterprise security and guardrails.
Okay, Section 1, why basic memory fails, and the limits of flat vector storage. Let's get right into it.
We need to shatter the illusion right now that basic retrieval, like standard RAG, is enough for a production agent. When you treat all memory identically and just dump it into a flat database, you trigger 4 cascading failures. First up is context poisoning. If an agent hallucinates a fact and saves it, well, that error gets retrieved later, creating this corrupted, self-reinforcing feedback loop. Second is context distraction. Your agent just gets flooded with semantically similar but entirely irrelevant noise, which completely dilutes its attention. Third is context clash, which is where the agent retrieves a user's old address and new address at the exact same time, leading to absolute confusion. And fourth is work duplication. Without shared state and proper logging, multiple agents will just repeatedly fetch the same data, wasting your token budget and creating a total observability nightmare.
Section 2, the 4 agent memory types. Cognitive framing for silicon brains. To solve those failures we just talked about, we actually need to map psychological human memory directly into our agent architectures. First, we have working memory. Think of this as your agent's active workspace. It's the prompt context window holding immediate conversations, streaming outputs, and temporary tool executions. It is incredibly fast, but remember, it is a purely temporary state. It's heavily restricted by token limits. If you don't actively manage this caching layer, critical information simply vanishes into thin air the moment the session ends.
So because of that, we need episodic memory to track what happened. This is basically the agent's personal diary. It logs specific past experiences, temporal sequences, and historical interaction traces across different sessions. This is how an agent maintains continuity with the user over time. It remembers not just what was said, but the exact sequence of events that led up to a specific outcome.
Then we have semantic memory. Now, unlike episodic traces, which are just event logs, semantic memory tracks what is true. This is your persistent knowledge base of verifiable facts, rules, and current world states. It persists indefinitely, and obviously it requires constant updating and versioning as your enterprise knowledge inevitably changes.
Finally, there's procedural memory. This acts as the automation engine. It's the encoded, validated skills and action sequences that let agents execute complex workflows, like your CI/CD pipelines or deployment scripts, without having to reason from scratch every single time. It is quite literally the muscle memory of your AI system.
Moving on to Section 3, architecting for scalability. From biological inspiration to software orchestration. Let's see how all this builds into actual production architectures capable of handling thousands of episodes. Notice the mammalian hippocampus analogy mapped here. It's actually super cool. Look at the transition from the red failure episodes into the yellow consolidation phase. The system uses an algorithm called DB-scan clustering to group raw episodic failures, like maybe repeated authentication or HTTP errors, and then consolidates them into generalized semantic rules during an offline sleep phase. This means your agent learns from its mistakes automatically, extracting the signal from the noise without requiring constant human intervention. Building directly on that, we have this modular production architecture required to make it all happen. The reflector module acts as an advanced monitoring tool, analyzing episodic failures and extracting root causes. Then, the abstractor generates a rule, and the dreamer creates synthetic test scenarios to verify it through execution. It is genuinely amazing to see a built-in, automated evaluation framework like this. It guarantees that new memories won't cause catastrophic forgetting of old skills.
Section 4. Knowledge graphs versus vector DBs. Semantic proximity versus verifiable truth.
Next, we absolutely have to address a major production trade-off: deciding how your agent actually stores and retrieves these semantic facts at the database layer. Vector databases offer high-speed retrieval based on fuzzy semantic proximity. So they're fast, but they're highly prone to approximations. Conversely, knowledge graphs, or graph RAG, use deterministic node relationships. They allow for strict schema validation and auditable multi-hop reasoning. Look, if you are building a low-stakes customer service bot, vectors are probably fine. But if you are deploying agents in healthcare or finance, you absolutely need the verifiable reasoning paths that only a knowledge graph can provide.
Section 5. Optimizing cost and latency. Hitting strict production metrics.
Engineering is fundamentally about constraints, so let's look at the hard data on how advanced memory architectures optimize latency and token budgets. You cannot scale a system if every single memory retrieval bankrupts your cloud architecture. 31 times. Just let that number sink in for a second. This represents a massive breakthrough using the hippocampus framework. By utilizing a mathematical shortcut called the dynamic wavelet matrix, this system bypasses costly, high-dimensional dense vector computations entirely. By doing semantic search in a compressed binary domain, it drives a staggering 31 times reduction in end-to-end retrieval latency. For a high-frequency agentic loop, this is literally the difference between a sluggish prototype and a snappy, production-ready product. And on the cost optimization side, we see token consumption reductions of 85 to 95%. This is achieved using the MGPT operating system metaphor. Instead of blindly stuffing the context window, the agent explicitly pages data back and forth between a cheap archival hard drive and its expensive core RAM context. This tiered caching strategy slashes token cost dramatically, all while keeping the agent hyper-focused.
The impact of these optimizations is completely undeniable. Check out this stark performance gap in complex SQL generation tasks. An agent with no memory succeeds about 33% of the time. Adding basic RAG pushes it to 65%. But an agent equipped with robust, active dreaming memory consolidation hits an incredible, perfect 100% success rate. Proper memory architecture isn't just about cost optimization, it is for sure the ultimate driver of task accuracy.
Section 6. Enterprise Security and Guardrails. Governing the agent's reality.
Finally, we must tackle the governance gap, because building a brilliant agent is completely useless if it violates your company's compliance policies. An unbounded, ungoverned memory pool is quite literally an enterprise security disaster waiting to happen. The first layer of defense is rate limiting the memory itself through selective forgetting. This is driven by the RFIR formula. Step 1 is recency, using exponential decay to phase out old data. Step 2 is relevance, ensuring cosine similarity to the immediate task. And step 3 is frequency, tracking how often historical data is actually retrieved. This mechanism strategically prunes noisy data to prevent your databases from becoming expensive, bloated landfills of irrelevant information.
But the true enterprise governance gap goes way deeper than that. Without a strict context layer, your system lacks data lineage, meaning you literally can't trace where an agent got a specific fact. You also need authentication and role-based access control, or RBAC, so the agent doesn't accidentally retrieve executive-level secrets for an entry-level employee. Furthermore, you must prevent context bleeding across multi-tenant boundaries and ensure complete GDPR deletion compliance. Without these guardrails enforcing strict access policies, your agent is just a massive liability.
So I want to leave you with this provocative thought to conclude our explainer today. Your agent might be reasoning perfectly, but is it retrieving the right reality? As we've seen, deploying production AI systems isn't just about clever prompt engineering. It's about architecting a rigorous, scalable, and secure memory foundation. So, evaluate your own infrastructure. Look closely at your latency, your observability, and your guardrails, and ask yourself, are your agents truly ready for the real world?